Alright, welcome to this video on organic chemistry. Today's topic is going to be isomers. So we're just going to jump right into some examples on isomers. And isomers are just compounds with the same molecular formula, but differ in the arrangement or connectivity of their atoms, okay? Iso means same. Let's write this down. Iso means same, okay? So we're going to have the same molecular formula, but something is going to be different, and there's different types of isomers. We're going to be talking about constitutional isomers today. Okay, so my name is Andrew, okay, Andrew Sanchez, and there's a billion other Andrews. There's Andrew Jackson, there's Andrew Dotson, there's Andrew Tate, okay? I'm me, okay? Even though there's a bunch of other Andrews, I'm me, okay? So all these other Andrews were isomers, okay? Anyone that has the same name, same molecular formula. Okay, so we're just going to start off with a couple examples. Okay, there's going to be butane, there's going to be N-butane. Okay, so the name of this guy, the molecular formula of this guy is N-butane. Okay, which we'll see, this is going to be an alkane group with 4 carbons. Okay, so N-butane is C4, H1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. So C4H10. This is N-butane. And by the way, another way of visualizing N-butane is every time we have a carbon, we're going to indicate these junction points just with the line structure here. So I'm going to draw this line structure like so. So namely, every time we have a junction point, that's going to be where the carbon lives. And all these hydrogens that live on the exterior are still there, but they just are invisible. Okay, this is just the bond line structure. And both of these are the same compound here. Okay, so this is N-butane C4H10, but there's an isomer for N-butane, which looks like this. Suppose we move the carbon from over here and move it to live over there. It's going to have a structure that looks like this. Notice that there's an extra H over here. Okay, and if we were to draw the line structure for this guy, it would look something like this, where again, each of the lines indicates where the carbon lives. Okay, and then this is going to be isobutane. Isobutane. Okay, so they're both C4H10, right? If I count 1, 2, 3, 4, that's still a C4. C4, and then let's count the H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is still C4H10. This is isobutane, so 2 molecules with the same formula, but they have different structure and therefore different properties. So isomers is going to be super important in the context of chemistry and biochemistry. Okay, and we're just going to do a bunch of examples to get used to seeing different types of isomers. Okay, next we're going to draw 3 constitutional isomers with the molecular formula C3H8O. Okay, and so constitutional isomer, right, means same name, different formula. So there's no special way, there's no algorithm for this. I'm just going to draw carbon bonded to another carbon, so that's C2. I'm just going to draw the other carbon bonded to it right next to it like so. C3, okay, I'm going to draw the oxygen right here with the OH attached to it just like so. Let's fill in the rest of those H's. I'm going to put 2 over here, 2 over here. Notice that every carbon needs to have a total of 4 bonds here. And in this case, this carbon has 3 H's attached to it. We have 1, 2, 3. This carbon has 2 H's attached, but then it is bonded to 2 other carbons. And then this final carbon has 1, 2, 3 bonds as well. So if we were to count our carbons, we have a total of 3 carbons, so that's C3. C3, let's count our H's. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we do have C3H8, and that 1O lives right there. Let's go ahead and draw that line bond structure. We're going to have a line for those two carbons that live from here to here. Another line for these two carbons that live from here to here. We don't need to draw these H's, but we do need to draw this OH group that lives right over here. So two ways of drawing the same guy here. This is C3H8O. This is our first constitutional isomer. Okay, the name for this compound is going to be propanol. Propanol, okay? And notice that we have an OL group here, so that's going to be an alcohol. Okay, maybe you've heard of this substance. As a matter of fact, I need to draw another carbon bond that lives right over there. So now we have a total of 1, 2, 3 carbons at each of those ends or junction points. So this is going to be 1 propanol. Now for our next isomer, suppose I move one of the OH groups onto the carbon over here like so. Then our bonds are going to be looking a little bit like this. Now we're going to have 3 H groups on the edges again. This carbon is still going to have 1 extra H. Don't forget that guy because everyone always forgets that guy. We're going to have 1 OH group that lives on the end like so. And if we were to try to draw the bond line structure, we would have something that looks like this. The carbon-carbon bonds like this. And then we're going to have a carbon OH bond like so. Okay, and let's count our carbons here. We're going to have 1, 2, 3 carbons. Let's count our H's next. 1, 2, 3, 4, 5, 6, 7, 8. So that's C3H8O. Okay, and then this is going to be called isopropanol. Okay, but notice that they are indeed isomers of each other. Same name, different structure. The last isomer is, suppose I have our carbon bonded to our oxygen directly here. And it's kind of hard to explain how I'm thinking of these. It's just a matter of practice. And let's see, if we have this bond line structure, it should look something like this. Notice that the carbons at the end don't have any H's because, again, these are invisible H's. It takes a little bit of getting used to see it, but over time you will start to see these invisible H's right here. So let's count our carbons. We do indeed have 1, 2, 3 carbons. We're also going to have our 1, 2, 3, 4, 5, 6, 7, 8 H's and our 1O. And again, we do have the same name, so this is going to be another isomer. The name of this isomer is going to be ethyl methyl ether. Ethyl methyl ether. Okay, so again, these are the 3 isomers of C3H8O. Same names, different formulas. Okay, for our next example, we're going to draw all the constitutional isomers with the formula C4H10O. Okay, so this time we're going to have 4 carbons. So just to give you a hint, there's going to be quite a few different isomers here. There's not going to be just 4, there's going to be more than 4 isomers here. So pause here and see if you can get a couple by yourself, or perhaps you can get all of them by yourself. Okay, and then the best strategy to go about this, I suppose that there is a sort of algorithm here. We're going to try to determine how many isomers we can have with just the carbons. So don't worry about the oxygen yet. Let's just do just the carbons. Okay, so we're going to have a linear branch with all the carbons connected to each other like so. And then suppose I also have another copy of this where I move one of the branches onto that carbon there. So 2 of these carbon structures here. This one we're going to call linear. And then this one we're going to call branched. Okay, now we're going to try to make this a little bit more systematic. And so first, rather than just kind of guessing and checking, let's just try to obtain where the oxygen is going to live. And suppose I just put the oxygen on the first carbon here. Let's label all our carbons. This is going to be 1, 2, 3, 4. And then we're going to label this guy as follows. 1, 2, 3, and then the fourth one that lives right there. Now we're going to have a couple different copies of linear and branch. So first I'm going to start off by having another copy of our linear guy. Like so. And suppose I just put another oxygen that lives right on that first carbon rather, right over there. Okay? And then suppose I have another copy and then put the oxygen in between the first and the second carbon. Right, because that's definitely possible. Okay. What other variations of this can we have? Suppose I put the oxygen in between the second and third carbon like so. So I'm going to make another copy. Okay, and then so that's going to be our fourth guy. Any other linear ones we can do? What if we have the oxygen rather not on the first guy but the second carbon here? So let's have one more linear copy. With our oxygen that lives right over here. And we are going to fill in these H's in just a moment. As a matter of fact, I encourage you to fill in those H's if you haven't already. But we're going to go ahead and do that again for the branch section here, just so we can do this a little bit systematically. Suppose I duplicate this. Okay, and we're going to do something really similar, where first I'm going to have one copy where the oxygen lives on that first carbon, like so. I'm going to have another copy where the oxygen lives on that second carbon. Okay, and then let's see. I think that's all the isomers we're gonna have. All we have to do is fill in the H's. We might be saying, well, why can't we put the oxygen on the fourth and third carbon? Well, if we do, we're gonna have copies of the exact same molecule. So that is not gonna be an isomer. That is going to be the same exact molecule. Okay, all we have to do now is just fill in the rest of these H's like so. So we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one is indeed C4, 1, 2, 3, 4, H10O. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and this one again is indeed another C4, 1, 2, 3, C4H10O. Now let's do this next guy here. We have 1, 2, 3, 4, 5, 6, 7, 8. Remember, all the carbons need to have a total of 4 bonds. Let's also add these lone pairs on the oxygen as well, since we're at it. Okay, so this is again another C4H10O. What about this guy here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a little bit messy with the annotations there, but hopefully you can see that this one indeed is another C4H10O. Okay, so we have 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it seems like we're missing one more, everyone. We have a total of 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6. We have a total of 6 isomers here, but we're missing one more, whereby we take another copy of our branched one here, and we put the oxygen right over here. There's going to be 1, 2, 3, 4, C4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C4H10O. Okay, and then here's 7 different isomers for that one single molecule, everyone, C4H10O. Okay, next we're going to draw the constitutional isomers for the molecule with the formula C4H10. Okay, so we're going to go ahead and do the algorithm method one more time, but if you want, we can guess and check because this one only has a couple here. So I'm going to start by drawing our linear formation here with C4 in a straight line like so. So this is going to be our linear structure, and then I'm going to draw the branch one where I'm going to move one carbon over here. Okay, so we're going to have 1, 2, 3, and namely I'm going to put the other carbon to live right over here rather. Okay, so right off the bat, hopefully you can see that we're going to have 2 isomers just like so, where we just fill in our H's. And if you were to count your H's, you would indeed have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 H's. So this one is C4H10. That's going to be N and butane here. Okay, and then if we fill in our carbons, if we fill in our H's here, we're going to have a total of C4H. Let's count our H's. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh dear, we're missing another H. And that's because we need to have a total of 4 bonds to this carbon. So we're going to fill that in with this H right there. So that is 2 isomers for C4H10. And as a matter of fact, this is all the isomers we have for C4H10. Okay, this is going to be butane and isobutane. Okay, next we're going to draw the constitutional isomers for C5H12. Okay, very good. And then so we're going to go ahead and do that sort of structure. Let's start with the linear formation of carbons. And I'm going to do one branch where I move one of the carbons onto this carbon like so, where we still have C5. Okay, and then I'm going to have one more. Suppose I have one formation where we have our carbon that lives not here but here rather. Okay, so we're going to have 2 sort of structures for C5 here. I'm going to start with our linear guy because this one's probably the most intuitive. So we have C5. I'm going to start by drawing out our H's like so. Okay, and okay, so this is going to be our first isomer, everyone. This is going to be called N-pentane. Okay, this is going to be called N-pentane. And then the next one I'm going to fill out is this one here. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is C5H12. So that's going to be our second isomer, everyone. Okay, the next one I'm going to do is going to be this branch right over here. Okay, we need to have this H that lives right here and all the 3 H's on the sides. Okay, so it's going to be 1, 2, 3, 4, 5. Okay, so C5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is C5H12, and then that's going to be our 3 isomers for C5H12. Okay, we're going to do one more example, and this is to draw all the isomers for C6H14 here. Okay, so we're going to start by doing all the branches. I'm going to do it systematically, just like so. So I'm going to have a 6-carbon chain. Okay, I'm going to have a 5-carbon chain. I'm going to put 1 carbon that lives right there. And I'm also going to have another copy of a 5-carbon chain. And then move this carbon, let's see, this is going to be 1, 2, 3, 4, 5, 6. So this is going to be a 4-carbon chain. I'm actually going to move this one down to the 4-carbon chains. I'm going to have another copy of the 5-carbon chain where I move that carbon to this carbon like so. And I think we're only going to have these 4 structures. And then suppose I have another copy of the 4-carbon chain where this guy lives like so. 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, so these are going to be our 1, 2, 3, 4, 5 isomers in total. Okay, and then all we have to do now is just fill in these H's. So people say that organic chemistry is kind of like a puzzle. This is what they mean. There's not really a direct way to answer this. Algorithmically, we just have to just intuit what are going to be the 5 isomers in each case. Hopefully you think this is kind of fun too. Just fill in those H's. And then just make sure we count our carbons as well. Let me move this out of the way because it's getting a little bit clogged right there. And the last step is we do have to go back. We should be counting our carbons and our H's every single time. But since this is the last example, I kind of wanted to just do them all in one go. But ideally, we should go ahead and do them one at a time. So going back to this guy here, we have 1, 2, 3, 4, 5, 6 carbons. Now when we count our H's, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is indeed C6H14. Next guy here, we have 1, 2, 3, 4, 5, 6 carbons. We're going to count our H's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, C6H14. Next guy here, 1, 2, 3, 4, 5, 6 carbons that live on this molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. C6H14 satisfies this molecule as well. 2 more to go. 1, 2, 3, 4, 5, 6. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 H's that live on this guy as well. Finally, last but not least, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, C6H14 there. That's going to be it for this video. Hope this was helpful. If you do need help for organic chemistry, I do offer private tutoring as well as group courses. So check all the information down in the description if you need to lock in for organic chemistry. Best of luck, and I'll see you in the next video.